Machine translation is the process of using artificial intelligence to automatically translate content from the source language to the target language without any human intervention. In this session, we will be discussing types of machine learning technique, various types of vectorization technique, what is RNN, how RNN works, what is gradient explosion, and why it occurs. We will also see how LSTM and GRU work, what is sequence-to-sequence model is, how the encoder-decoder work, and how the teacher forcing mechanism works. In this course, we will be solving one use case of machine translation where we will be creating a model for translating English text into French. So without any further ado, let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Hello everyone, my name is Shrikant Kumar and I welcome you all to this tutorial on machine translation. Today in this tutorial we are going to cover what is machine translation, what are the various types of machine translation techniques available. Then we will be looking into some of the NLP concepts which we use predominantly in deep learning. Then we will be covering what is sequence to sequence model, what are the various types of sequence to sequence model available. Mostly we will be covering encoder-decoder model, and then we will be looking into teacher forcing techniques. Then we will be solving one machine translation use case. So without wasting any time, let's get started. Let's start with introduction to machine translation. For this, we will be taking an example. Suppose you work in a MNC firm and your company wants you to go from India to France to attend a business conference. And the thing is, you don't know any other language other than English and your native language. So suppose they gave you a boarding pass and they asked you to travel to France. So now you boarded the flight and you, after 12 or 13 hours, you reached France. And now the moment you reached there, you felt that you are hungry. Okay. So now you are feeling hungry. So then suddenly you saw a pizza outlet there. So the moment you entered the pizza outlet, you saw everything is written in French because it's a France. So a natural that most of the things will be written in French. So everything is written in French, and you don't have any other friends who knows French, and they are with you. Okay. So what will you do? The moment you get the menu, you started scratching your head. So then suddenly you got an idea that yes, you can use the Google Translate or Bing Translate or any other translate application. So you open your browser and then you typed the keywords that are written in French, and then you can translate them into English and then you can order it. Okay, so this make your life easy. So this is all about machine translation. So machine translation is a field of AI which enables or which gives the ability to a machine to translate your language from like from one language to the another language. So some of the examples of AI driven machine translations are Google Translate, Google Assistant, Facebook Translate, Grammarly, Siri, Alexa. Then there are a couple of browsers which allows you to translate whatever written in a browser from one language to another language. Now let's discuss some of the machine translation techniques available. One of the most predominantly used or most widely used machine learning translation technique is statistical machine translation technique. So what is statistical machine translation and how it works? So let's see. Statistical machine translation uses parallel corpus to train a machine translation model. So what does it mean? Let's say there is a language X and there is language Y. Okay. And we want to translate from X to Y. Let's say X has A, B, AB, AC, C, D. The corresponding values for Y would be, for the training set would be, let's say 1, 1, 2, let's say 1, 2, 1 1 2, then it will be 1 1 4, or let's say 1 6. Okay, then C would be 6, or it would be 14 1 4, then D would be 9. Okay, and so on. Okay, so there will be, for each corresponding data points, there will be the value for Y. Okay, so it will translate in such a way that for X, what is the data point, and corresponding data point present in Y. Okay, so this way it will translate the or it will train the model. Okay, so the goal of SMT is to translate a sentence from source language to a target language. So mathematically, suppose that we want to translate a Hindi sentence, that is Y, given a sentence X that is written in Tamil. Okay, or the that the speaker is speaking in Tamil. Okay, so this will use this formula, that is nothing but a Bayes theorem. Okay, so it will be, if we just elaborate it, it will be arg max of Y, P of X, Y, and P of Y. So this will be your probability, or we can say uh, machine translation model, and this will be your language model. Okay, so let's try and understand how this function works, okay, with an example. So let's suppose Rohan was supposed to study with me. I called him, but he did not. Then there is a blank. Okay, now suppose we want to fill this word and want to complete the sentence. Okay, so based on the probability of this word, or the most suitable word, we can find out with the help of, let's suppose we have corresponding corpus: answer, well, good, go, study, have. Okay, and then there can be more words like that. Okay, so like with did not, what is the word whose frequency is highest? Okay, so if we see and since we know English language, so we can understand that have has the highest frequency. So if we write did not have, okay, so with the probability, we are able to fill this the next word, but is it making sense? No, this is not making sense. Okay, so what can be the answer? So let's suppose that highest probability was answer. Okay, so in that sense, answer is the correct word which we get. Okay, so there is a probability, or we cannot say that it's a fixed that we will get the correct next word which will fill this blank. Okay, we can fill it with have, we can fill it with go also. Okay, so it has been seen that although statistical machine translation model works well, but in some of the cases it does not perform well as it is expected from it. Okay, so in order to tackle this issue, we have a model that is known as neural machine translation model. Okay, now let's see what is neural machine translation model. Okay, so SMT model was very complex, and we saw with the example that some of the time it does not perform well. Okay, so then come neural machine translation model. Okay, so neural machine translation model uses sequence to sequence architecture, which involves two RNN. Okay, then encoder encodes the sentence and feed this encoding to decoder, and then decoder produces the target sentence. Okay, so let's try and understand this. Okay, so what happens that there is a input. Okay, so this goes to a black box. Okay, this is a black box. Okay, so this black box is neural machine translation. Okay, and for that input it gives you output. Okay, so now further break this down. What is happening? Let's say we have input. Okay, this input goes to here, this sequence to sequence model. So here we have encoder, we have decoder. So I'll just write E and D for the same. Okay, so it goes to encoder, then encoder encodes it, send it to decoder, and then decoder decodes it and produces the output. Okay, further, how this happens, let's elaborate it furthermore. So encoder encoded it into a contextual vectors. Okay, and that contextual vector goes to decoder, and then decoder decodes it and gives us the output. Okay, we will go and discuss this, what is the structure of encoder, what is contextual vector, and what is decoder, and how it produces the output, what how input goes there. So we will discuss those things later in this slide. Okay, so we just wanted to discuss that what is encoder decoder on a broader picture. So before we go and discuss what is a sequence to sequence model, let's recap and try to understand the natural language processing concepts in deep learning. So there is a concept of text vectorization. Any machine learning model, be it uh, random forest, be it logistic regression, or it's a CNN, or it's a RNN, LSTM, GRU, you name any model, they work on numerical data. And since NLP deals with textual data, so we need to transform our the textual data to a numerical data. So text vectorization is technique with the help of which we can transform or we can convert our text into numbers. So some of the predominantly used or most important text vectorization techniques are bag of words, TF-IDF, word embedding, and character embedding. So, what is word embedding? Or let's start with what is bag of words. So, bag of words is nothing but bag of word is a technique in which from the entire text corpus, let's say we have a raw data, and then we do the processing. Okay, we do processing, and after processing we get a data. Okay, so this text data will go into a box. Okay, for understanding, we can understand that it's a bag. Okay, like a bag of coins, it's a bag of words. Okay, then there each word will go, and corresponding their IDs will be there, so that whenever we want to identify or we want to convert that from text to number, we can convert it. Let's take an example. This is car, this is my bat. Okay, so what will happen, each word, this is a car, since this is already present and is also present, my will be the next term and bat will be the next term. So correspondingly they will get some values or they will get some IDs to uniquely identify them. Let's suppose it will get 1, it will get 2, it will get 3, this will get 4, this will get 5, this will get 6. Okay. Then suppose there is a new term comes. This cat is not mine. Okay. So when we will translate it into vectors, what will happen? This will get 1. Cat, since we don't know cat, and in our vocabulary cat is not present, so it will get 0. Is will get 2. Since again not is not known to the model, so it will get 0. And mine is also not present known, so this will get like this. Okay. Like similarly, if we translate this car is mine, how we will get the vector form for that? This will get 1, 2, 3, 4. Similarly, this will get 1, 2, then 5 and 6. Okay. So this way we do the transformation using bag of words. Okay. So let me erase this. So now let's try and understand what is TF-IDF. So TF-IDF stands for Term Frequency Inverse Document Frequency. So what it does in a very crisp words, we can understand that those documents which are present in the corpus and they have less frequency of occurrence will get higher precedence or will get more weightage than those words whose frequency are higher in the corpus. Okay. So now let's move on to our next slide. What is word to vec? Okay, so word to vec is a word embedding technique. Okay, now we discussed a bag of words. Okay, so what typically happens that in bag of words or in any normal model when where we are uniquely giving IDs to each token and then we are creating it. Let's suppose that we have a corpus. Let's say C is the corpus that has total 10,000 unique words present. Okay, and if I write this is my bat. Okay, so what will happen? We will get a 1:10,000 size vector. Okay, so this will be translated something like that into there will be some values. Okay, similarly, let's suppose a total number of document we have 1 lakh. Okay, so the vector size or our vector will be cross 10,000. Okay, so this will be a sparse matrix. Okay, so this sparse matrix is very difficult to pass through the model and train a model which can perform well. Okay, so in order to tackle those issues, word embedding came into picture, and one of the techniques of word embedding is word to vec, where we, instead of uniquely identifying or uniquely giving weightage to each word, what do? We do the word embedding or we do the word to vec with the help of features and the word. Okay, so let's suppose the how it works, we can understand that there is king plus boy minus queen. Okay, so what does this means? Okay, so to word embedding or to word to vec, since we are passing king. Okay, so king has certain properties. Some of the properties would be power, army, land, money. Similarly, gender of king. Okay, similarly, boy has certain properties, like what is the color, where to which location he belongs, who is the father of this boy. Then similarly, like what is his gender. Okay, since like this is male, and minus queen. That means this person is not female. Okay, so predominantly we can say that he is prince. Okay, so this is the way by which word to vec work. Okay, so there are two types of word to vec available. One is C bag of words and character based bag of words, and another one is skipgram word to vec. Okay, now let's move on to our next topic, that is character embedding. So, character level embedding uses character level composition and provides a numerical representation of words in one dimensional convolutional neural network. Okay, now let's try and understand what is RNN. RNN stands for recurrent neural network. Okay, so why RNN came into picture? Before we go and discuss the architecture behind this and how it works, let's try and understand why RNN came into picture. So before RNN, we had CNNs. Okay. So in CNN models, they are very good with the image kind of a data, or data where we don't need the information from the previous state or the from future state. Okay, so if we have the present state, then in those cases CNN works well. Now let's take an example of text data. Suppose you are watching some Marvel series movies. Okay, now, since you know that the Avenger series, in Avenger series, what kind of like what happened in the last season or what happened in the last movie, based on that you can understand that what are happening in this situation. So now suppose we train a CNN model on top of that. So since CNN model does not know or does not hold the previous information, since they don't have any holding technique, or they don't have the memory, so what typically happens that in CNN models, they do not perform well with the text data. So in order to tackle those issues, RNN came into picture. So RNN stands for recurrent neural network, as we discussed. So RNN has a memory state to grasp or to hold the memory. So if we try and understand that what happens here, so in any RNN cells, okay, we have two inputs. One is our input vector, and the other one is hidden state. Okay, so if we try and understand it, what happening here, that there is a input, then there is, once a model start, it starts with hidden state 0, or we can say h0. Okay, so this input vector 1 goes there. Okay, so these goes to the model. Okay, so this model, and then correspondingly your output will be generated. Okay, and your hidden state 1 will be generated. Okay, so this continues. So if we see here in this example, let's say this is nothing but a, we can say a breakage, or how this works. It is shown here if we unfold it. Okay, so it starts with ht minus 1 hidden state when t minus 1, the input vector goes there. Okay, and xt minus 1, the hidden state goes there. Okay, and we get output t minus 1. Then this vector goes here, and this xt will goes there. Okay, this will generate qt, then qt plus 1 will be generated in this state when we will be providing ht plus 1 and xt plus 1. Likewise, it holds the previous information and the previous state. This enables, or this allows the RNN to keep the information with itself. Okay, so this way RNN outperform CNN in textual data. Okay, now let's move on. But we have seen that there is a exponential gradient problem in deep learning. So what is exponential gradient problem? Exponential gradient used to update the weight in the right direction with right amount. Okay, so when your model is training, so with the help of understanding that how much your model is not performing well, error gradient are used to update and to just tweak the model weight to make it like better, so that it can perform well. Okay, so in RNN, during training, some of the time what happens that this RNN, this error gradient accumulate and may update the weight with very large gradient. Okay, so as a result of it, we see a like explosion. Okay, this explosion disturbs the model's state. Okay, and due to which models completes training, although but it does not perform well as it is expected from it. Okay, so in order to tackle those issue, then LSTM and GRU came into picture. Now let's try and understand LSTM. Before we go and discuss the architecture of LSTM, let's try and understand LSTM with an example. Suppose you are watching television. Let's suppose you are watching FIFA. Okay, it's a match between Portugal and Argentina. Okay, so then suddenly your mobile phone starts ringing. Okay, and look who is there. It's Rohan. Okay, and Rohan is calling you after a very long period of time, that is 5 years. Okay, so the moment your mobile starts ringing, you pause your or you mute your TV, and then you pick up the call. Okay, and you started conversing with Rohan. Okay, so what did you do? First, you stopped the television or you pause the television. So by this, what unintentionally you did, you just get away from the state where you were there, and then you start conversing with Rohan. Okay, then you guys started discussing how did you guys studied during the college, and how is Professor Sumanto, or how is like Roop sir is doing and all. Okay, so then the moment you guys started the conversation. Okay, so what happens that with the all the information or the data which Rohan is providing you, then you're recalling those things. Okay, and based on those recalls and based on those information, what you started responding to the opponent or to Rohan. Okay, so now let's understand the same example with this LSTM architecture. So this is known as cell state. This is known as your forget gate. Okay, so this is the cell state where you were there before talking to Rohan, watching television. Then this is forget gate. The moment you started conversing with Rohan, you decided what to keep and what not to keep. So you decided that I will not be watching the match. So you stopped the match, or you stopped the information which you are getting from the live match. Okay, so this is how gate works. Then there is another gate that is known as your input gate. Okay, so based on the forget gate, okay, you decide that it's a sigmoid function. Like you decide that what to take and what not to take from the information which Rohan is giving you. Okay, so this is your input gate. Then based on that input from Rohan, you update yourself. okay, and you got to know what is happening in your college. Let's suppose how is your teacher is doing, or let's say how your mentor is doing. Let's suppose that how your Anjali ma'am is doing. Okay, so you got to know from Rohan that now she is in Massachusetts. Okay, so these kind of information you are getting, and based on that you are giving the response. Okay, so this is the output. Okay, so LSTM has three inputs or three gates. One is forget gate, which allows you to keep certain information and to what to keep and what to remove. We can do it with the help of forget gate. And then input gate is with the help of forget gate and the previous state, you can take a decision which information to keep and which information not to keep. Okay, so this is the input, and with the help of this input and all, you can update your output. Okay, and then you can give it. Okay, so this is your next state, and this is the cell state. Okay, so it's a same. Then there will be one LSTM set, then there will be one LSTM and one LSTM, and it will go on till how many units you want to keep for the LSTM. Okay, so this is the basic functionality how LSTM works. Okay, so now let's move on to the next slide. So GRU is also similar kind of a model. Okay, but it has only two states. One is reset, and another one is known as output. Okay, so it has opposite to or not similar to LSTM. It has only two output. One is update, okay, which does update your values. Okay, and reset is doing the same thing, like what to keep and what not to keep. Okay, and then it gives you y hat and the output and the next state. Okay, so then there will be one more GRU attached to it, then there will be one more attached, and then similar to LSTM architecture, it is same. But GRU and LSTM works similar to each other, but GRU has only two gate, that is update gate and reset gate, but LSTM has three gates: forget gate, input gate, output gate. Okay, so what is sequence to sequence model? Till now we have covered the basics of natural language processing, which we use in deep learning. Now let's try and understand what is sequence to sequence model. So, in order to solve complex tasks like language translation, creating a chatbot, text summarization, question answer system, sequence to sequence model works very well, or it has been seen in various fields where sequence to sequence model works best for this. Okay, so encoder decoder architecture is one of the most common sequence to sequence model architecture available in the market. So there is one encoder, so it encodes the output and gives a context vector, and this will go to decoder, and then decoder will give you the output. So this is the basic structure of how encoder and decoder works. Okay, so now let's discuss them briefly. So before we go and discuss encoder and decoder, let's discuss some of the real life examples of sequence to sequence model. Some of the examples which we use in our day-to-day life is Google Translation, Google Assistant, Siri, Grammarly. Then we use Google's Smart Compose. We use Android Smart Keys. We also use Alexa. Okay, these are some of the sequence to sequence based models use case which we use in our day-to-day life. Now let's discuss how encoder-decoder model works. So this is the basic structure of encoder-decoder model. So encoder-decoder model both uses RNN. Okay, so it can be LSTM or it can be GRU. Okay, so these can be the RNN models which we can use in decoder encoder, but we need to keep in mind that if we are using LSTM, then we cannot use GRU here. Okay, we will use only LSTM. okay? Or if we are using GRU, then we will not be using LSTM, okay? We will be using GRU, okay? So now let's try and understand how this encoder-decoder works, okay? So we can have a box, something like that. Let's call it encoder denoted by E, okay? And we have a decoder, the same as shown in the picture, that is decoder denoted by D. And it has few RNN states, and similarly this has few states, this, okay? Now suppose I want to feed a input, okay? Let's write how are you, okay? And this gives you a output, I am good, okay? So first this how will go, okay? So I'll just mark it 1, this as 2, this as 3, okay? So the moment this will, how will go to this, okay? This 1 will go, then this H1 is generated, that is hidden state 1, okay? So then this will go to the model, okay, as shown in the picture. Then similarly 2 will go, okay, then this 2 will go, okay, and it will generate H, and this will generate H2, then this H2 will go, and then this 3 will go, okay, and this will generate H3, okay, H3, and this H3 will be your context vector, we can say, or we can say encoder vector, okay, as shown it here, okay, and this will go to this, okay. So the moment it will go here, it will generate I, okay, then this will go to the next context, it will generate M, then this will go to the next context and it will generate good, okay. So if we see closely in this diagram, what we can see that in the second box or the decoder, we have the outputs and we have the next hidden state. But in this, if we see closely in this encoder, we don't have the output from this RNN. So the RNN architecture of encoder is such that they don't produce the output, okay, and we don't or we can say we don't store the output here, okay. Instead of that, we provided the hidden state, okay. So this is the basic structure of how encoder decoder works, okay. So now let's move on to our next slide. So encoder decoder using teacher forcing. So what happens that when we train our model, okay, so sometimes this happens that encoder decoder model takes very long time to process, okay. So encoder decoder model are known for taking very longer period of time to train, and some of the time they overfit itself, okay. So in order to tackle that, we use the teacher forcing. So how teacher forcing works, that when this hidden state 3, let's say H3, goes to this, okay, to this encoder vector, okay, this encoder vector, let's suppose that this is H3, it goes there Y1. Similarly, there is one output, this is your decoder input, okay. So this is your encoder input. We do not directly give the X1, we do the embeddings, okay. So be it word to word embedding, like be it word to vec, be it character based embedding, be it one hot encoding embedding, anything, okay, bag of words embedding. But we do provide this encoding to this x1, x2, and x3 are nothing but the input vectors. Okay, so this goes there. Similarly, this decoding input is nothing but the input vector for the decoded, the correct output. Okay, so this goes there. Okay, so the moment it goes there, and the moment it predicts, let's suppose that it predicts y11. Okay, and then it checks with this decoded input that whether the output which it is generating is correct or not. Okay, so our correct output is y1. Okay, so the model will penalize itself. Okay, the optimization technique will start working, and it will penalize the model. It will do the like update the weights of the RNN model, and then it will refit itself so that it can generate y1. Okay, so this way we get the better result by applying teacher forcing in encoder decoder model, and it also stops model to getting overfit, as well as it helps us in, it reduces the time taken to train the model. Okay, so let me erase this. Now let's move on to next slide. So what are the drawbacks of encoder decoder model? So it has been seen that the encoder decoder models have limited memory. Okay, so since we are using LSTM, okay, so it can perform well with longer text, but this cannot work well if we are passing an entire like sentence, or a sentence is containing 100 lines of text. Okay, in such situations encoder and decoder model not perform well. Okay, similarly, model does not perform well when the length of the string is greater than 10. Okay, so with the help of blue score, in various researchers researched, and they found out that with increase in word length, the blue score started decreasing. Okay, so blue score is the parameter with which we can judge the performance of any encoder decoder based model for machine translation. So this has been seen that with this it starts reducing, the blue score starts decreasing. So in various researchers found out, after performing various research, they found out that if the word length is greater than 10 or is 10, okay, it does not perform well. This is not a thumb rule, but this has been seen in various situations. This can be opposite of that for some of the cases when our data is different. Okay, since we know that machine learning or deep learning model works on data. Okay, if your data is correct, model will perform well. If your data is not correct, model won't be able to perform well, whatever technique we can try. Okay, so this depends upon the type of data as well, or the data and the frequency of the words. But it also has been seen that with a longer string, a model does not perform well. Okay, now let's try and solve a machine translation use case using Python programming language. Here we will be using encoder decoder based architecture with teacher forcing, and for this use case we will be using English to French language translation dataset that is freely available in kaggle.com. You can use this link to download the data. So now, without wasting any time, let's get started. So first, we will be loading the packages that are necessary to doing all the pre-processing stuffs. So we will be loading pandas and numpy. So now we have downloaded this data from the kaggle.com. So now let's upload this data. So we loaded the data, and now let's see. So there is a English word, corresponding to that we have a French word or a sentence. So like for example, hi, and corresponding to that there is salute. Okay, run, then course. Okay, and then I'm not well versed with French words, so I'll prefer not to spell them. Yeah. But we can understand from this data that for each data point in English, there is a corresponding data point in French. Okay, so like we discussed in statistical machine translation model, that it's a parallel corpus. Like for X, there is Y. For X, there is Y. Okay, now let's move on. So what we will be doing first, we will be identifying, or we will be finding out the length of the string. Okay, so with the help of a string function, we will be first splitting them into a chunk of words, and from those tokens we will be counting the length of them. Okay, so let's take an example how this works. For example, let me create a, so this will create a list. Okay, so what it will do, it will create all the words into a tokens, and that tokens will be stored into a list. Okay, and then this str.length will do str.len. So let's execute it. It will take some time. So it will find out that how many words are present there. Let's, for example, let's see, there is one word, so it will count one. Okay, so now let's execute it. Okay, similarly we'll execute it for French also, and now let's see the data. So now we can see that there is English word count and French word count. Okay, so for the sake of this encoder-decoder model, and we know that encoder-decoder model does not perform well when the string length are very large. Okay, so for this purpose, we are strictly using the length till 5. Okay, so if anything that is greater than 5, we will not be using those data points for training and for testing our model. Okay, so now let's execute it. So if we see, earlier we had 1,76,621 data. Now we have 54,212 data. Okay. Now there can be a situation that we have a duplicate data, and when we have a duplicate data in our model, we need to drop them off. Otherwise, there can be a situation that our model will be overfitting. So with the help of drop duplicate function of pandas, let's execute it. Now let's see how many data. So we didn't have any duplicated data. So now we have our data ready. Okay, so now let's divide the data into train and test. Okay, so before dividing the data into train and test, let's just understand basics of how train and test split works. Okay, so let's suppose this is our entire data. So this is our data. Okay, let's say it has 100 data points. So in our unique data, let me write it unique. Okay, so from those unique data, first we divide the data into train, and as well as we divide it into test. Okay, after dividing the data into train and test, let's suppose that we divided it into 80 and 20. So 80% will be the train and 20% will be the test. And since we are using train test split, so our data will be stratified sampling. That means the proportion of the data would be same. Okay, there won't be a situation that one type of data would be in train and the other would be on the text. So there will be a mixture of the data. So now we have this 80-20 ratio ready. Now this further we can divide it into further train and validate. So this can be 80% and this can be 20% of that, so that we can train the model, and for validation and for optimization of the model we can use this 20% of data. And once our model is ready, then we will be using this 20% of the data that is totally unknown to the model. The model is not knowing about that data. That data is unseen to the model, and based on that data we will be try and will try to find out that whether our model is performing well or not. So this is the best technique whenever we are dealing any machine learning or deep learning model. Okay, so we need to divide the data into three parts. First, train, test, then that train will be further divided into train and validate. Now let's divide the data into train and test using train test split. So we have divided the data into train and test. It will take some time. Now let's see how many words are present in train set, how many French word maximum present in text set. So it would be 5 because we are not keeping those data points whose word length is greater than 5. So now further we will be dividing this train data into train and test with test size as 20. So we have divided it. Now let's calculate the this word frequency of English term and French term. Okay, that is available. So let's execute it. Now we have this is this English and French frequency words of CSV file ready. This takes typically 10-minute time or something like that. So I had already executed it, so I'm not going to execute it. So instead of that, I'll just load this data and now see. We can see that in English, the words and their frequency, okay, and the frequency is such a way that the highest frequency terms is get on the top. Okay, so it's a decreasing in the order of decreasing frequency. Okay, similarly the French keywords are there. Okay, now let's do the data pre-processing. Okay, so whenever we are preparing the data for any machine translation model or for any sequence to sequence model, we provide a start token. Okay, let's say start, then whatever is our input, then we provide the end. Okay, so this we do with all the data. Okay, so that the model will understand what from which point of data the model is starting and from which part of the model it is stopping. Okay, so to know the start and end of the data, we provide two anchors, that is start and end. Similarly here we are providing start and end to raw lines. Okay, so we are using the whatever the data we are getting, to that data we are appending it with the start and end. Okay, now let's see. So if we do this, we can see it in English that every sentence that start, I am just a teacher, end. Okay, are you getting tired, start, end. Okay, likewise we will do it with the French word also using this get word function. So let's execute it. So now for each French words, we have that start and the end string. Okay. So now we will do the for the validation data also. We had did this with the train data. So now let's do it with the validation data. Now we have the validation data ready. Okay. So now since we are using the frequency of words maximum of 5, okay, and there can be minimum of 1. Okay. So what will happen if our input is 1? So let's say that the token gets for high. Okay, the high term will get uh, frequency. Let's say its token ID is 1. Okay, so it will be 1. Okay, then there will be some term whose like number of tokens are present 1, 2, 3, 4, 5. Then there will be 1, 2, 3, then 1, then 5, then 5 and 4. Okay, and things like that. Okay, so how can we normalize them, or how can we just fix the length of each of the terms? Okay, so to do so, we use the term padding. Okay, so we pad the each term after it, and we can do it with the pre and post. Okay, so here we are using post. Okay, let's say there is two tokens, 240 or 254 and 2. Okay, then there are three spaces. Those three spaces will be occupied by, let's say, 0. So 0 is our padding. So after once the string gets completed, this will be filled with the 0. Okay. So we are using the tokenizer from Keras. Okay, and then we are creating a token, this frequency token, French token, English token. Okay, and then we are training it with the French trained word and English trained word, and then we are creating a padded sequence for each of the terms, like for English and for French. So now in the next thing, what we are doing, we are finding out the number of input token, number of output token, number of what is the maximum length of input and what is the maximum length of output. Okay, so let's execute it. This will take some time. Let's execute this also. So now it is executed. Let's execute it. So now we can see that each of the terms are getting at the end 0 is appended. Okay, now let's execute this. Now let's count the number of output tokens. So number of output tokens are 17187. Number of input tokens, that would be around 10,000. Now let's see what is the input length, maximum input length, that is 7. What is the maximum output length? That is also 7. Okay, now let's see French train word. Okay, that was something which I'm not very comfortable in reading. Now let's see the padded of French. So we can see this frequency of this. So this process is good, but we have a very good package known as ktext. Okay, so we will be using this ktext package to do all the data pre-processing. Okay, so this ktext package is you can download it using pip install ktext. Okay, now let's import ktext function. So now we have imported process. Okay, now we will be doing the cleaning, we will be tokenizing, and we will padding the each text. Okay, for this we are using all the keywords, that is 10407, and maximum padding length we can assign any values, but for now we will be assigning it to be 7. Okay, and then we will be creating a train vector. Okay, so it takes a longer time to process because it does all the cleaning, tokenizing, everything. Okay, so I'm not going to execute it because it takes around half an hour process. So this way we can create a pre-processing for English. Similarly, for train vector we can generate. For French also we can do the same thing. Okay, and once we are done with that, since we will be using this preprocessed vectors into whenever we will be deploying this model, or if we want to do the prediction with this model, so we will be keeping those values into dpickle files as well as numpy files. Okay, for saving it into a pickle files, we are using dpickle. Okay, that is dill. Okay, and we are using numpy to store it as a numpy vector. Okay, so since we have not executed the uh, above two portions, so I'm not going to execute this because once we get this train vector and this preprocessed files, then we are dumping them into English pp, French pp, similarly French trained vector and English trained vector. Okay, so once we do that, why did we do that? Because let's suppose that this takes around 1 hour to process. Okay, and now suppose when we have a data of 20 crore, what will happen with those 20 crore? Let's suppose it takes 6 hours to process. Okay, will we do each time this 6 hour will invest in pre-processing? No. So what we will be doing, we will use it for once. we will invest those 6 hours, and we can use the same file each and every time. Okay, that's why we have stored it into a pickle file, that is serializable file. Okay, whenever we want to use it, we can use it. Whenever we don't want to use it, we will not import it. Okay, so suppose whenever we want to load those data, okay, so this data, the numpy file, now we want to load that decoder input. Since we discussed that we will be using the teacher forcing, so we need the decoder input. While discussing the architecture of teacher forcing with in encoder and decoder, we discussed that why decoder input is important. Okay, so we will be loading it. So once we load it, we will be getting the decoder input data as well as decoder target data. Similarly, we will be loading the encoder input data. Okay, so we will be getting the encoder input data as well as the doc length. Okay, so in order to load the any pickle file, the dpickle files which we have stored already, okay, we are using this load text preprocessor. Okay, so we will be passing the dpickle file, and that dpickle file will be opened, and we will get the total number of tokens and the processed file. Okay, so it is returning that number of tokens and the pp, that is English pp and the French pre-processed. Okay, so now let's execute this. Now let's execute it. Now load it. Okay, since we have not loaded the dpickle, okay, so let me just copy it. So let me just add it here. Okay, so we will be loading the dpickle. So now we have loaded it. Okay, so the number of vocabulary in size of vocabulary is 6280 for English vocabulary, and the French vocabulary is 9998. Okay, now let's import the vector files. Okay, so with the help of load encoder and load decoder, we will be loading them. We will be getting the encoder input data, decoder input data, the doc length, and the decoder target data. Now let's see how it has been processed. Okay, so for this French input, we get the text vectors. Okay, similarly for this English, we are getting the original text, and the after pre-processing we can see it. Okay, now for this model training and model building, we are using Keras. We will be using GRU. Okay, so now let's import the packages. Now let's create a encoder model and decoder model. Now let's try and understand encoder and decoder model, how we can write a code for that to create a encoder and decoder. So for this, we are using the embedding as 300 dimensional embedding. Okay, so our embedding is 300 cross 300. Now let's define the encoder model. So encoder model shape would be the doc length, that is 7. Okay, and we are saving it with the name of encoder input. Okay, now this encoder input will go to the embedding. That embedding has the number of tokens, the dimension of the embedding, and we are storing it to body word embedding. Okay, and we are passing this encoder input to it, and then we are doing the batch normalization. So that X will go to the GRU. Okay, and since it's an encoder, so like we don't need the output from the encoder, so we are not keeping the output from the encoder. We are just storing the next state. Okay, so that's the next state is there. Then we are building a encoder model with the help of model API. Okay, we are passing this encoder input output as a state h, that is the output will be the last state or the context vector. Okay, and then we are creating a sequence encoder output, that is encoder model to this we are passing the encoder inputs. So this input which we have created here, so that we are passing it here, and with this we are creating encoder output. Similarly, let's define our decoder model. So for that decoder model, we are passing the shape as none, okay, and we are keeping the name as decoder input for teacher forcing. Okay, since we are using teacher forcing, so we will be passing this decoder input to the decoder model. Okay, then we are creating a word embedding for decoder. Okay, that is, we are passing the number of decoder tokens, latent dimension, and we are naming it with the decoder token, and we are passing the decoder input to it. Then we are doing the batch normalization, and then we are creating a GRU model, and we are this is our GRU model, and to this GRU model we are passing the batch normalized output. Okay, we are storing it here, and initial state is our the sequence to sequence encoder output, because we know that how encoder and decoder works. Let me just draw it. So there is a encoder and there is a decoder. So this last state from the encoder, that is context vector, goes to this decoder. So this is nothing but that context vector. Okay, so now let's see. We have now we have that decoder output. Okay, so now we will doing the batch normalization for that decoder output, and then we will be passing this to a dense layer, and we will be using a softmax as a activation function, and then the model like we are storing it to a this decoder output by passing this x to this decoder dense. Okay, now then we are creating a sequence to sequence model. That is model, here we are passing the encoder input and decoder input as a output. Okay, and decoder output as output. Okay, these are our input, this is our output, and then we are compiling the model with loss as sparse categorical cross entropy. Okay, so now let's execute it. Now our model is ready. Now let's see how the model architecture looks like. So this is our model. Then what we are doing it here, we are just uh, creating a model checkpoint and CV logger. Okay, so why model checkpoint we are using? So now let's create a sequence to sequence model and train it. Okay, so before training the model, we are storing the loggers into CSV logger file. Okay, that we are creating a CSV logger that is with the name of tutorial sequence to sequence dot log, and we are saving it into as local, and then we are creating a model checkpoint. So what model checkpoint is? Model checkpoint checks each and every iteration of the model, and till now the best model, whatever the best model is, we will be saving that model only. Okay, so by this way we just keep the model which performs better irrespective of storing the overfitted model or the underfitted model. Okay, so this way we prevent the model to get overfitting and underfitting. Now let's see, for batch normal batch size we are using 1200 batch size. Epochs we are using 70 epochs, and that whatever the model history is during the training, we are storing it to history variable. Okay, so now let's execute it. So this takes usually this takes a longer period of time, so we can wait for some of the times, and we will not be keep the model running for 70 epochs because this takes time. So for that, what we have already done is we have trained the model completely, and the best model which was with us, we saved that model only. So for now we will be training the model for let's say, because this will take 1 minute time, and then if we keep on running for 70 epochs, this will take around 90 or 80 odd minutes. Okay, so I'm just stopping it for now here. So just keyboard interrupt. Okay, now let's delete this sequence to sequence model object. Okay, since we have stopped it at a bit middle. Okay, so now we will again create a sequence to sequence model object using this model, where we are passing this encoder input, decoder input, and decoder output, and we are compiling the model. Okay, so our model is ready. Now we can see the model dot summary. So we can see the same summary of the model. Okay, total number of parameter, what are trainable parameter, what are non-trainable parameter. Then we will be loading the model weights. So what typically happens that whatever the weight has been assigned to the model while training it, we have stored it, and that we will be feeding it to the architecture of this sequence to sequence model. So now let's execute it. So now we have our model loaded with that. Okay, so now we have our, since we have already trained it and we have loaded the weight to the model. Now let's see how model has performed. Okay, so for that we will be extracting the encoder model and we will be extracting the decoder model. Okay, so first, for that encoder model, let's create a function extract decoder model. Then we are passing the entire model. For this we will be passing this sequence to sequence model. This will give us encoder model dot get layer. Okay, if we go up, we can see that while defining the model, to each model we name them. Okay, let's say encoder model. Okay, so we will be calling the model with the name encoder model and we are returning this encoder model. Similarly, we are extracting the decoder model by providing the decoder word embedding. Okay, then we are just extracting the decoder input, decoder embedding, decoder batch normalized. Okay, and at the end we are extracting the decoder model. Okay, so now let's execute this function. So now we have extracted this. Okay, now we will be creating a sequence to sequence interface. Okay, so what this will do, this will get the input from a user. Okay, and this will give a output that is in French. So it will take a input in English and it will generate a output in French. Okay, so now let's see, here we are using all the encoder pre-processed, decoder pre-processed things. Okay, and we are initializing a init function. Okay, that will get all those values. Okay, maximum length of the French word, maximum length of the English term. Okay, and things like that, everything. Then model, we are loading this sequence to sequence model here. Then we will be creating a function to generate French. Okay, so what it is passing, it is passing self, it is passing the raw input text, that is nothing but the English term. Okay, the English text, for example, hi, hello, how are you, this kind of a text. Okay, then it will be passing a maximum length of French. For default it is none. We will be getting this with the help of this default max length French. Okay, so now if the max length French is none, keep the max length as self dot default max length French. Okay, and if you provide while calling this function, if you provide any number, let's say 10, 20, 30, that will be the maximum length of French keywords. Okay, now we are loading the raw tokenizer. Okay, for English we are using this pp English dot translate. We are providing this raw input text. So the moment we provide the raw input text into a list, or in the form of list, it will translate and give a tokenized vector for that. Similarly, this raw tokenized input will go to the model, okay, the encoder model, and it will predict the encoding body for that. Okay, this body will we are storing it as a original body encoding. Okay, Then we are just doing a set state value. Here what we are doing, we are using this French tokenizer, okay, to token id to start, okay, and then we are reshaping it to 1x1 vector, okay. Then decoded sentence, stop condition, for now it's a stop, false, okay, while not stop condition, till we do not get a condition for which our stop condition will be true, it will iterate, okay. Then it will predict and state, okay. Then self dot decoder model, then predict, okay. We will pass this state value as well as this body encoding or original body encoding, we are passing it and it is predicting it, okay. Then that prediction will be, we are getting the maximum prediction value, since we are using softmax, okay, while creating the encoder and decoder model. So it will generate each words, it will not generate the text, rather than instead of generating the tokens, it will generate the probability for the token, okay. And that probability, we are getting here the maximum probability, okay. So with the help of np.argmax, we are getting that token whose frequency is highest, okay. And that token, that id will, we will be passing to id dot token, okay, and that will give us the predicted word for that, okay. And until or unless if we get that predicted stop word as end, okay, or the we reach to the decoded sentence is greater than or equal to the maximum French word, we will change the stop condition to true and break it, okay. The moment it breaks, it will go and it will break the loop, okay, and then it will not execute these states, and at the end we will be getting original body encoding join decoded sentence, okay. So this way we are generating the French, okay. So now next we are creating a function that is known as print example. So here we will be passing the English text and the French text, and we will be seeing that what is the predicted output French text for that, okay, so that we can understand that whether our model is performing good or not, or how it is performing. So now let's execute it. So we have created a class for that. Now we will create the object sequence to sequence INF, create it, okay. Now we will be using this uh, this demo model prediction, okay. Here we are passing the df, so that df is nothing but our test data. So now let's see our test data is. So our test data is this has 10,000 some values, okay. So we are not passing the entire 10,843 values. Instead of that, we are passing the 50 data, okay, and df is equals to test data. So now execute it. So uh, let's see, it takes a couple of time. So now here is our English text, okay. I'll be the 17th next year. Then the original text is this. For this we can see that this is the text for that, okay. And we can see that our model has predicted this start and end, okay. So we can see that our model has not performed well for the first case. Now coming back to the second case, we can say what a beautiful town, okay. So now we can see that our model has performed well. So we are getting a good result here. I don't smoke, so it is also again giving us a correct result. Then if we see this example, our model is not performing well. Now if we see this example, our model is performing up to some extent, it is performing well. For the last keyword, it is they are different, okay. It is giving us the same result, okay. So if we see the results, we will see that for some of the data the model has performed well, but for some of the data it is not performing well. Okay, so this is not the best model, but yeah, we can tune this model, or we can add and remove the tokens whose frequency is, let's say, 1. So with a frequency of 1, we know that the word has occurred only once in the entire corpus. So we can remove those tokens, and then we can retrain the model, and that model will outperform this existing model. And then we can do some of the architectural changes, and let's say we can use attention into that, we can use beam search into that. So we can do various kind of a thing in this model and get a good result for that. But for this use case, our intention was to just build a sequence to sequence basic model and try and see how the results are coming for a machine translation model. Okay, now we have concluded our syllabus, or we have reached to the end of this tutorial. So now let's recapitulate whatever we discussed. So in this tutorial, we discussed what is machine translation. Okay, then we saw some of the examples of machine translation, like Google Translation, Siri, and things like that. Then we discussed what is SMT, or statistical machine translation, and how it works, and when it works well and when it fails. Then we also discussed what is neural machine translation. We discussed some of the NLP concepts. Okay, like what is word to vec. Okay, what is bag of words. Okay, how RNN came into the picture. Then we also discussed what is LSTM. Okay, long short term memory. Then we discussed gated recurrent neural, that is GRU. We discussed what is gradient explosion in RNN. Okay, and how LSTM and GRU prevent it. Okay, we discussed these things also. Then we discussed what is encoder decoder based models. Okay, what is teacher forcing in encoder decoder, and how we implement teacher forcing. Then we implemented a encoder decoder based model in Python with teacher forcing. Okay, with the help of Keras, and we built a English to French translation model. Okay, so that's it from this video. I hope you enjoyed this session, and you got a clear picture about what is machine translation, how machine translation works, what is encoder decoder based model, how word to vec works, and things like that. Okay, so till then, keep learning, keep growing.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.